Hopefully I'm recording. All right. Okay. I can't decide what to do today, so I'm going to try to do both things, and they'll both kind of suck because of that. Okay, so I want to start to really try to take only 10 minutes to talk about the ingredients of class field theory, in general. So what I tried to do for the first 3 lectures was talk about how class field theory works in the case of QP, the p-adic numbers. And that's a very, very restricted setting. And actually, the same kinds of tools work to do class field theory over a really large class of fields. So I want to just really quickly kind of tell you how things would have to change for that, and then I'll switch gears to Kummer theory. Okay, so abstract class field theory ingredients. So what you really need to do class field theory is just some G, a profinite group. And what I mean is that your G is some inverse limit of, I don't have that in my notes. I don't want to use a finite indexing set. I don't know. Okay, I'll put H. Okay, no, I know what I can do. No, I'll do H. Okay, so where H is finite. Right, all of those, right? So a profinite group just means you have a bunch of finite groups that you got from somewhere, and then you take a projective limit of them. And actually, though this feels abstract, any profinite group, it's actually always the case that such a group is the gamma group of some separable closure over some field. So that's not actually more general than talking about Galois theory. And then the thing that you need to kind of get the whole thing going is a set A, which is a continuous multiplicative G module. And what that means, right, so G module means you're acting on it by G, so you want nice action things. So the identity of your group on an element of A should give you A. The multiplicativity, so A has some multiplication operation, and then you want that to agree with the G action. And then comes a little bit of an awkward situation here. So you want to also be able to multiply in G, but really the G action should be on the right, and I'm writing it on the left. So that's why I have to switch the order of the tau and the A. If you've ever wondered why there are right and left actions, is because of the order in which the applying the G elements has to happen. And then finally, you want that this set A is given by the union of all the open subgroups of G. Over all the open subgroups of G of this A upper H, where A upper H is the sets of elements in A such that sigma A is A for all sigma in H. And these open subgroups of G, they are, when you think of G as being the Galois group of some separable closure, they're exactly the Galois groups of K bar over K for a field big K of a finite degree over little k, right? So the idea, just like the separable closure is built out of finite extensions of little k, like, I mean, it's an infinite extension, but made of just all finite things that are getting bigger and bigger, right? You also want your set A on which G is acting to be built out of the fixed fields of kind of like finite extensions of your base field little k. And for us, in everything that we did, you know, for 3 days, right, the A was just K bar cross, right? Or I mean, and you know, we were even more specific than that. It was QP bar cross because we were talking about QP, the p-adic numbers. So in the case of local fields, right, so QP is a local field, there's a kind of like really easy module, which is kind of just the field itself or the non-zero elements of the separable closure that the Galois group acts on just like normal, right? Like Galois is on its fields. And so these fixed subsets, right, they're just the finite subfield, right? The finite extensions of QP. And you're just saying that A, you know, the big separable closure is, you know, the union of all the finite extensions there, right? And the difficulty in the global case, right, so QP is a local field because it has one prime. Q, the rationals, is a global field, has many primes, is to find, right, this set A that you can act on. And those are the Adels. Like, that's one reason to learn about Adels is like they're the ingredient that makes the whole machine go. And then you need just 2 more things, you know, not just G and A, but you also need any way to value the elements of the Galois group, right? So in the case of QP, we just looked at, you know, the restriction of elements on some unramified extension, and then they gave us a Frobenius, so that was the map. So, but in general, you need that. You need a continuous, right, way to judge the elements of the field. And you also need a compatible way to judge the elements of your set, right? So for us to remember, right, A was QP bar cross, and that was just like the normal valuation, like how much are you divisible by some prime. So you need that as well for it to work, and it needs to be compatible with this D map. Well, so it has to have 2 things. So first, the valuations have to contain the integers. They have to have like a nice quotient. It has to kind of look like Z hat in some way. Like if this was a surjective map, right, Z hat mod NZ hat would be Z mod NZ. But you also need this formula that for any finite extension, when you take the norms, so this is A, H, and H is the Galois group of K bar over K, right? So like these ones, like these kind of like finite parts of it, or the finite extensions, if you want to think of it that way, right? So like when you take the norm group of some finite chunk of it, it has to agree with the D map like this. Yeah. Okay, and this is a statement that I actually proved in the case of QP. If you like go back, I had like a little x and QP and like in some extension, and we wrote it as a prime, and then we, you know, calculated what would happen to it to check that this was true. And so like that's stuff that you need for class field theory. And that's it. Once you have those 4 things, and then one condition on these things being well behaved, then all of class field theory happens. So like the class field theory axioms. Okay, you should have that for every finite cyclic extension L over K, right? And here we have, you know, L contains K, and this is all over like the base field that we're working on. When you take, you know, you can think of like K cross here in the local case, whatever replaces it in general, mod this norm map that should have size exactly the degree of L over K, right? So this is some kind of statement that the norm map behaves well, that there's not, you know, too much stuff going on. And you also need that if A is an AL of norm 1, then A is sigma, right? So here, a finite cyclic extension means that the Galois group of L over K is cyclic, generated by some sigma, so that A is sigma B over B for some B in AL. And that's all you need. That's all that we used. We didn't really prove all that much. But if you have, you know, some set A to act on, and it, like your action of it is nice enough, and there's some way to value the group elements and some way to value the elements of that set A, then you get class field theory. Then you get, you know, classification of the billion extensions of your little field K, your little K, which is the base field there. You just like put it in the machine and it all works in the end. All right, so that's all. I wanted to do it in 10 minutes and it took me 13 minutes, so I guess it's not that bad. Woo. Okay, so that's not really what I want to talk about, but because I won't have time to do any global class field theory, like I felt like I needed to at least gesture at the what the theory would be, right? And just to repeat, if you were talking about like extensions of Q, for example, like that would be the Adels of the field K, that would be the Adels of the field L, and that's why I imagine it's called A. Okay. So now I want to talk a little bit about Kummer theory to connect with quadratic reciprocity. So in some sense, it's kind of like we're starting over. So if you know, got lost, which is fine, you can come back. Welcome back. All right. And so here, the axiom that we need for Kummer theory to work, right, like the main fact is that for every finite cyclic extension L over K, if I'll write the general axiom. A is an AL with norm 1, then A is sigma B over B for B in AL, right? So just the second axiom of class field theory. So like whenever you have a class field theory, you also have Kummer theory because Kummer theory requires less stuff. And today I want to do like a very specific example of Kummer theory. Today we'll have the group G, right, be the Galois group of some separable closure of some field. And the set A still be just K bar cross. So same situation as we were in the local case, except I'm not necessarily assuming that K is the local field. And in this particular situation, right, if A is the units in the separable closure of some field, actually the axiom is always satisfied, and that's Hilbert 90. Okay, so in this case, axiom is always satisfied. This is Hilbert. Okay, and always satisfied, like I mean, okay, any field. Okay, so we're good. We're good. We can do this, what we're about to do. There's no restriction. Well, there's going to be one restriction. Like right away, I'm going to put a couple restrictions on it. All right, so let's put ourselves in a situation, right? So we'll fix some integer n, positive integer, and we'll assume that mu n is contained in K. So mu n is the set of nth roots of unity, and K is some extension of my little k. So like, for example, if you want to be thinking of like little k being q, right, then you wouldn't be able to do Kummer theory for more than like n is equal to 1 and 2 over q, right? If you wanted to do like a higher n, you would have to pass to some extension that has the roots of unity in there for things to work. Okay, and what is a Kummer extension? A Kummer extension of K, right? And here an extension, I mean like a field extension is of the form K, and I adjoin the set of all nth roots of some subset of K cross, right? So I take like some non-zero elements, because like I don't want to do that, right? So I take some set of elements in K, and I just take like all nth roots of all elements in this set delta. And that's what we call a Kummer extension. It's like a set generated by nth, a field extension generated by nth roots. Let me bring this. Come on. All right. And such an extension is Galois with Galois group of exponent n. And what this means, like a group of exponent n, it means that for all g in this Galois group, g to the n is the identity, and n is the least positive such integer. Yep. Sorry, can you repeat? I couldn't hear the beginning.
Is delta a subset or?
A subset. It could be infinite. Like that, yeah, this doesn't need to be a finite extension. Or you know, it could be like several nth roots. Okay, and one way to see this you can have a map from this Galois group to the nth roots of unity, sending oh, sorry. So here I do mean just one element, right? So for A in that set, right? So, okay. So here I am talking about a whole set, and you take all the roots, and maybe that's infinite, right? But like everything in Galois theory, like every infinite thing that we built is built from like finite things. Like they're not like infinite in any bad way, right? So what I want to show is, so every, you know, little element in this big Galois group, right, I can restrict it to some, like just taking like one nth root of one element in delta, and I can send the sigma to sigma of root n, the nth root of A divided by the nth root of A. And that's like an nth root of unity. And so that shows you that if I raise this to the n, then I would get the identity. So, you know, it would go to the identity here. This is a group homomorphism, so every element in the Galois group had to have like order, at least dividing n. Okay. So the classification theorem here, right? So a Kummer extension is an extension with Galois group of exponent n, and the classification is that every Galois extension of exponent n is a Kummer extension. Classification theorem. Right? Like the goal of class field theory is to tell you something about extensions, like how do you get these extensions, how many are there, what do they look like. So in Kummer theory, allows you to classify like a certain very restricted kind of extensions. So if L over K is abelian of exponent n, then L is generated in this way, and also the set of roots that you take are exactly the intersection of all the nth powers in L, right? So you look at everything in L and then you raise it to the n, and the ones that land in K, like those are exactly the roots that you took to get L from it. Yeah? Mm-hmm. Yeah, sorry if I didn't write that. Yes, with abelian. so focused on the exponent. Yes. So the proof, like the general proof, right, with the set delta having many different elements, like reduces to just proving it for one element and then like taking compositums. So I'm going to work out the proof for L over K finite cyclic, right? And in that case, we get that L is K adjoint alpha with alpha to the n in K. And like to be clear, right, like so this is kind of the meat of this proof, but then you do stuff to like extend to your set delta having more stuff in it. But the extension is not like as illuminating as the proof of like the meat case. Okay. Ah, yes. Sorry, I reworked this proof a lot in my notes, and I have to figure out where the good part is. All right, so, okay, so L over K is a cyclic extension. It means that the Galois group is cyclic generated by one element. And I'm also going to give myself zeta a primitive nth root of unity. Right, so it generates the set of nth roots of unity. And remember that I'm assuming that the roots of unity are in K, right? So actually, this zeta is in K. So the norm of this zeta from L down to K, right, when I act on it by Galois, I only get zeta back, right? And this Galois group has order n, so I get zeta to the n, which is 1. Now, my axiom of Kummer theory was that when I have an element of norm 1, it's of a specific kind, right? So by the axiom slash, I mean Hilbert 90, because I'm not just assuming it's true, right? This means that zeta is sigma alpha over alpha for some alpha in L cross. That's where the axiom comes in, that every element of norm 1 is of this specific kind. Okay, so this tells me, right, that inside of K, there's this, containing K is this extension K alpha, and that's in L. All right. Now, if I multiply both sides by alpha here, I get that sigma alpha is zeta alpha. So sigma to the I alpha is zeta to the I alpha, right? Because every time I apply sigma, I get an extra zeta. And zeta is in K, so like it just stays, like sigma doesn't do anything to it. Okay, but this zeta is a primitive nth root of unity, so sigma I of alpha is alpha if and only if I is 0 mod n. Right, like it only is allowed to come back after I've applied it n times. So this tells me that this alpha has n Galois conjugates in K alpha. So the extension K alpha over K is of degree n, which is the same degree as the degree of L. So they have to be the same extension. Okay, so K alpha over K has degree n, but so does L over K, and so L is K alpha. And now I have one thing left to prove, which is to show that alpha to the n is in K. Now, if I apply sigma, still the generator of this Galois group, to alpha to the n, and I divide by alpha to the n, right, what I want to show is that ideally this is 1, right? Because this is a field automorphism, sigma is a field automorphism, I can write this as sigma alpha over alpha to the n. And sigma alpha over alpha, that was zeta to the n. And zeta to the n is 1. So sigma of alpha to the n is alpha to the n, and alpha to the n belongs to K. Because sigma generates the whole Galois group, so if alpha to the n is fixed by sigma, then it's fixed by the whole Galois group, and the fixed field of the Galois group is exactly K. I just thought it was like a really neat application of this weird axiom, like, oh, if you have norm 1, you're of a certain kind, like you're like sigma of alpha over alpha, and then you just like pop a root of you know, like just like this happens like almost by magic. All right, so with this classification theorem, you can get like a one-to-one correspondence between, you know, certain, maybe I'll write it. I was like, oh, I want to save time, I'm not going to write it. But I think talking about it is going to take more time. As a consequence, if, you know, the GCD of the characteristic of K and n is 1, and the nth root of unity and roots of unity are in K, there is a one-to-one correspondence between the groups delta that contain all nth powers in K and the abelian extensions of K of exponent n. Which is kind of a baby case, right, of this like classification of abelian extensions that we get from class field theory, right? So what we got from class field theory was like all abelian extensions of QP corresponding to like some open subgroups of QP cross. So these particular open subgroups of this kind, right, give you abelian extensions of exponent n. It's like a restricted version of like the bigger class field theory correspondence. But it you know, I like baby cases because you can see better what's happening. Oh my gosh, yeah, okay. And under this correspondence, the set delta that goes with L is exactly the nth powers of L that are contained in K. And so I'm going to say actually the same fact in two different ways. You can say that the Galois group of L over K is isomorphic to the set of homomorphisms from this set to the roots of unity, right? So you always want to kind of kill off the nth powers in K, right? Because like it's like if you took Q adjoint square root of 4, right? Like that's still just Q, so that's not like a new extension, right? So if you took Q adjoint cube root of 27, like that's still Q, right? So you never want to be taking like nth root of n powers, like that's not going to give you a new extension. So that's why we don't want to consider those, right? Or you know, we don't want them to interfere. Okay, so this is nice. That also tells you the Galois group of the extension, if you know kind of, you know, which roots you've taken. But another way to think about it is that the homomorphisms from the Galois group of L over K to mu n is isomorphic to delta mod this set. Delta mod K cross to the n. All right. So we finally get to define the Hilbert symbol now that we've done all this work for so long. So still the same hypotheses. Oh, but now we're going to be in the local case. Okay, so we're still, I'm going to take this. Okay, so hypotheses from now on. Right, so still that the characteristic of K is different than N. Mu n is in K, and then we want K to be a local field. And that's not quite exactly the set of local fields, but you can think of K being a finite extension of QP, or K being the real numbers or the complex numbers. Those are some local fields. There's like more local fields. Actually, there's, you know, these are all characteristic 0. So why would I say this, right? There are local fields of characteristic P that you're welcome to think about if you want instead. Okay, and now I will fix L to be K adjoin all the nth roots in K, right? Like if you want to think of n is equal to 2, right? You know, you just like put in like all the square roots, like all of them. Take the square root of every number and just like throw it in there. So this is the maximal abelian extension of K of exponent n. Right? Because every abelian extension of exponent n is taken by taking nth roots. So like if you take all the nth roots, like that's the biggest one you can get. Okay, so a fact that I won't prove, that should be proved. Right? I just want to be clear, like that's not obvious, right? It's not like, oh, I'm just telling you that and you can think about it in your head. But I do have only like actually 6 minutes left, so you know we're not going to prove it. This norm group of this L is actually all the nth powers in K. So by class field theory, right? Because now we're in the local case. We have that the Galois group of L over K is isomorphic to K cross mod K cross to the N, right? So that was the reciprocity law. Every Galois element is some Frobenius, and you can send it to some prime over there, and there was an isomorphism if you mod out by the norm group of L. So that's, you know, since the norm group is there, right? So that's like the reciprocity law for this extension. And that's why it's important that we're working with a local field so that our A set is K cross. If I was trying to say this over Q, I would need like some Adele situation there, which I don't want. Okay, so I have this fact. So that's class field theory. And Kummer theory told me this one. Right? Oh, but here, right, for my L, that's K cross. Right? So in Kummer theory, it was like a general L, but for the particular L, the maximal abelian extension of exponent n, this is the right thing to put there, right? And so this gives me, we get the Hilbert symbol. Wait, let me just move. So I have like just a little bit more room. Okay, so it takes two entries, and then you put the prime, right? So this is like the prime of K, right? K is a local field, so it has one prime. You put it there. If it's R or C, you just imagine that you're putting a prime there. From K cross, mod K cross to the N. K cross to the N, right? So those are the two things, the two inputs to the symbol going to the nth roots of unity, right? But what you do is that like this first K cross mod K cross to the N is going to be this one, right? So you think of like a sigma in the Galois group of L over K. And you think of the second K cross over K cross, mod K cross to the N as this, right? So some chi, which is a map from the Galois group to mu n. And then, like, I mean, chi takes a Galois element and sends it to mu n. So if you have like a chi and a Galois element and you want a mu n, you just like chi the sigma. Yep.
So where is our prime coming into play in the symbol?
It's the field K. Right, the field K has like a prime, yeah, right? So, oops, right, the way we talked about reciprocity, to every Galois element, we could assign like some norm of a prime, right? So some element in K cross, so we're going the other way, right? If we have some element here, we find the Galois element that it corresponds to, and then Kummer theory there's, if we have like a little b here, we get a homomorphism, and then we like apply one to the other. And let me do like one little example to make this a little clearer. So if I have A and B in K cross, right, I could take the reciprocity map of this extension this is like K cross mod, like the norm group of this extension. Okay. Okay, so okay, it's back. I take my little A there, I find the Galois element in this Galois group that it corresponds to under the reciprocity map. And then, oops, the Hilbert symbol of AB on P I don't think that there's a root. Yeah, no, just that. That was a typo in my notes, right? Is whatever root of unity A does to the root of B, right? So like the A gives you a Galois element because you're in this extension generated by root B. This Galois element multiplies the nth root of B by some nth root of unity, right? So this Hilbert symbol is like what root of unity sigma A does to the nth root of B. And that's not obvious, right? That's like something that you prove when you have time. I'll say just one more tiny thing. When n is equal to 2, right? Mu2, that's just plus or minus 1. That's in QP, right? So we don't need to deal with any extension. Then P, A on P, right? Because the prime of QP is P. That's the usual Legendre symbol. So that's how you get to quadratic reciprocity from there. Then I had like a little, like one path to proving quadratic reciprocity, but I think I'll just end here so we can have a little bit of a break. And I think that in the computational part of it, I'll tell you a little bit about explicit class field theory, right? So we have this correspondence between abelian extension and these like open subgroups of the Adels or whatever. But like say you want an abelian extension, like for yourself to take home, like a concrete one. That's actually really hard, even with class field theory. It's not telling you how to make the extension. So there are some cases in which we can do it. And so I think that's what we'll try to compute. All right, that's a blank one. And that's all for now.